Okay, good evening everyone. Today we'll be starting with the week 5 assignment. So today will be live session 5. The course is Natural Gas Engineering, week 5, assignment 5. The tutor for this course is Dr. Pankaj Tiwari. He is from Department of Chemical Engineering, IIT Guwahati. And myself, I am TA for this course, PMRF TA. My name is Vishal Dhawan and I am also from IIT Guwahati. So first we go into little quick revision of quick 5 contents. First is the what are the separator functions? Primary phase separation. Liquid hydrocarbon, it separates liquid hydrocarbon from gas. Next is refining by removing entrained liquid mist from the gas. Next, refine by removing entrained gas from the liquid. It will be separating liquid mist from the gas, and it will also be separating gas from the liquid. And this it will discharge separately gas and liquids, no entrainment. The main components of separator are centrifugal inlet device. This is the primary separation. It gives primary separation of liquid and gas. Next is large settling section of sufficient height and length. It is also called disengagement section to allow liquid droplets to settle out of the gas stream and to adequate search for slugs of liquid. Next is mist extractor or eliminator near the gas outlet to collapse small particles of liquid. Other parts, controller, it maintains the level of the liquid. Then liquid dump valve, when the level gets above a certain point, then the then it gets out through the liquid dump valve. Then gas back pressure valve is also there. Then there are safety relief valves, pressure gauges, glass gauge, instrument gas regulator. See, you all have done all this in your class, so I won't go into details. So this is just a quick recap. So write down. I'm giving you 2 minutes. Then we'll go to this next slide. Okay, we'll go to the next slide. It is selection of separator type is based on several factors. First is characterization of production stream to be treated. Next is floor space available at the site. The main criteria is the floor space available at the site. Next is the cost. There are three types of separator: vertical separator, horizontal separator, and spherical separators. Mainly vertical and horizontal separators are used in the industry. Spherical separators are used where there is a space constraint, but it is not used so much. Vertical separator, the main features are it is used for fluid streams having intermediate GOR, that is gas oil ratio, for large slugs of liquid, and it occupies less area, but the fabrication is little costly. Next is horizontal separator. It is widely used for high GOR wells. It is uh, for wells having high gas oil ratio. Next is it is much greater gas liquid interface. The interface for gas liquid separation is much more. Next is horizontal double tube separators. It is another type of horizontal separator. Horizontal double tube separators. It is of low cost and have higher liquid capacity. Next is spherical separator. It is an expensive and compact separation arrangement. Very limited search space and liquid settling section. Liquid level control in this type of separator is critical. It is very critical to maintain this liquid level control in this type of separators. So write down these basic points, then we'll go to the next slide. Then I have some of the diagrams for other different types of separators. Then we'll be going head down to the numericals right away. So just giving you 1-2 minutes, you note down if you find anything important in this slide. Write down because theoretical questions may also come from this type of notes. So it's not that the course is based on only on numericals. Theoretical part is also there. So try to write down everything what is there here. And do let me know if in between, if anytime the slides are not visible or my audio is not clear, just open your mic and let me know, because this I'm not, every time I'm not visiting this Google Meet site, I am on my slides most of the time. So if you text me, I may not notice every time. So it's better if you just, if you find any problem, if you just unmute yourself and let me know. Next is here I have shown different types of separators. As in the left, you can see this vertical separator. See the liquid gas interface. Then there is a gas gravity settling section at the top. Then there is liquid collecting section in at the bottom. Level control, you can see there is a level control valve. And there is a gas outlet valve also. Mist extractor is also there. Uh, it absorbs the mist which is present in the gas, and it reduces that, and it pours down on the interface. The liquid collected there pours down on the interface. Same is the horizontal separator. You can see this liquid out valve, this liquid control valve is also there. Then there is pressure control valve, or the pressure control valve attached to the gas outlet. Mist extractor is on the right side of the separator. Then there is gas settling section. Gas liquid interface is there. Then liquid collecting section is also there. There is a inlet diverter, as you can see. There in both the inlet diverter, it gives a first, it gives a change in velocity to the first flowing stream. This provides initial separation. This liquid inlet diverter, that provide a liquid initial separation. So if you want to draw this, you can draw this quickly. I'm giving you 2 minutes, then you can go down to the next slide. Okay, I am going to the next slide. Here you can see there is a double interface horizontal separator. double tube separator is there, then there is spherical separator. Just draw the diagrams. Okay, we'll go to the next slides. Then there are three-phase separator. Here, oil, gas, water, three phases are commonly used for well testing. And in instance, the sweat-free water readily separates from oil or the condensate. Three-phase separation can be accomplished in any type of separator. The three-phase separator separation feature is difficult to install in spherical separator because of limited space. So in vertical and horizontal separator, in both the separator we can separate three phases. The factors which mainly affect separation are separator operation pressure, separator operating temperature, and fluid stream composition and quantity. These are the three factors. Then we need to do while designing the separator, we do flash vaporization calculation. It is used, it is done to get optimum, to find the optimum pressure and temperature so that we can get maximum liquid recovery. If operating pressure is more or the operating temperature is less, then the liquid converted in the separator is more. So, so flash vaporization calculations are very important in designing separators. You can write down this point: operating pressure more or operating temperature less, liquid converted in separator is more. And our aim is to get more liquid in the separator. Okay, we'll now start the numericals. The first question is a vertical separator under the following condition of flow of oil flow rate to 2800 barrel per day with gas oil ratio of 900 and operating pressure of 8 psig. We have the first question is the gas flow rate equal to number option A 2.8 mmscf per d, option B 3.1 mmscf d, option C 2.52 mmscf d, option D 0.32 mmscf d. A vertical separator under the following condition of oil flow rate of 2800 barrel per day with gas oil ratio of 900 and operating pressure of 80 psig will have the gas flow rate equal to 2.8 mmscfd, 3.1 mmscfd, 2.52 mmscfd and 0.32 mmscfd. Just try once from your side, then I will be solving it. Okay, so is there any answer? Anyone who tried to solve it? Shubham, Prajwal. Okay then. I hope you have written down the question, so I'll be solving it. So flow rate is given as Q equal to 2800 barrel per day. GOR equal to 900 SCF per barrel. Flow rate of gas equal to 2800 into 900. So it's very easy. It will be 252 SCFD or 2.5 mmSCF. So the correct option is 2.52 mmSCFD, option 3. Write down the numerical, and then we'll be going to the next question. So we'll go to the next question. The liquid settling volume of the four options are: option A 49.20 barrel, option B 24.71 barrel, option C 10.67 barrel, and option D 1.94 barrel. The liquid settling volume of the separator. The liquid settling volume of the separator. These are the four options. Try once from your part, then I will be solving it. Okay, the liquid settling volume of the separator, 4 option 49.20, 24.71, 10.67, and 1.94. Okay, let me read the name again. Anyone, any answer you have? Okay, then let me solve it. Formula for that is 1 W equal to 1440 into V into T. W is the flow rate of the liquid, it is 2800, then 1440. We have to find the volume. The time we will be taking as 1 hour, as it is not given in the question. So we will be taking as 1 hour. Let us check. So if it is not given in the question, we will be taking it as 1 hour. Or if it is per day, anyway, we will be taking it. So if you solve this one, the volume should come out as 1.94. So this is the answer. The correct option is option D, 1.94 barrel. Okay, so write down this numerical. Once you are done, please let me know. Then I will proceed to the next question.
Yes, sir, done.
Okay. Okay. Then next question. Question number 3. A gas is flowing at a rate of 8 SCF per day through a separator of diameter 1.8 feet. A condensate of API gravity 67-degree API is flowing at a rate of 25 barrel per SCF. The operating condition is 850 psi G and 78 degree Fahrenheit. Considering gas compressibility factor to be 0.8, K equal to 0.21, and density of gas to be 0.042 lb per feet cube, and density of liquid is 54.5 lb per feet cube, determine the gas capacity at standard for a vertical separator. The four options given are 50.4 SCFD, number B 72.62 SCFD, number C 115.60 SCFD, and number D is 150.95 SCFD. Try once from your part, then I will be solving it. Okay, I will be solving this question now. Formula for that is QST equal to 2.4 into B square into K into P divided by Z into T plus 460 density of liquid minus density of gas divided by density of gas. So P equal to 78 degree Fahrenheit, P equal to 850 psi, 1.8 feet square, density of L equal to 532 Lb per feet cube, density of gas equal to 0.042, Z equal to 0. Z, how much it is given? The value of Z is given as 0.80, 0.8, and K equal to 0.21. So if we put this in this formula, it will be QST equal to 2.4 into 1.8 whole square into 0.21 into 850. Can you just hold on for a second? Sorry for the delay. Okay, so where have we got? Yeah, so next will be 2.4 into 1.8 into 0.850. Then bottom it will be Z is 0.8 into 78 plus 460. 460. So this will be into this another part, which is 54.2, which is the density of liquid minus 0.042 density of the gas divided by 0.042. I hope my handwriting is understandable. If there is any problem or any query, just let me know. Try to solve this and try to get the answer. Okay, so the answer I'm getting is 115.8 equal to this is equal to 116. So this so the correct option, okay, the correct option is 115.60. That is the nearest to our answer. So correct option is option C. Just write down the numerical quickly, then we will go to the next question. Okay, let's go to the next question. A natural gas field is producing 125 mmscfd per day of gas of specific gravity 0.7. The wellhead pressure and temperature are 100 degrees Fahrenheit and 480 psi respectively, and the fluid density and formation volume factor are 1.65 lb per feet cube and Bg equal to 0.034 feet cube per SCF respectively. The separator operating conditions are 170 psi and 105 degree Fahrenheit respectively. The mixture contains 0.5 weight% water. Density is 62.1 lb per feet cube. Viscosity is 0.63 cp and 7 weight% hydrocarbon liquid. Density is 54.15 lb per feet cube. Viscosity is 0.78 cp and the remaining is gas of density 0.68 lb per feet cube and kinematic viscosity is 0.012 cp. The hydrocarbon liquid hold up and search time are 24 minutes, 25 minutes and 5 minutes respectively. These are the data. So the first question is the fluid mass flow rate per hour at wellhead condition is option 1 0.3 into 10 to the power 5 lb per hour, 2.9 into 10 to the power 5 lb per hour, 7.1 into 10 to the power 5 lb per hour, and option D 9.5 into 10 to the power 5 lb per hour. So write down the question. Write down the question and try from your side once, then I will be solving it. Okay, now I'll be solving it. So the formula is W equal to 125 into 10 to the power 1 10 to the power 6. So we have to find the mass flow rate, right? So it will be 125 into 10 to the power 6 SCF per day. We'll change it into mass. Next will be 1.65 the LB per feet cube into 0.034 feet cube per SCF. So it will be SCF feet cube will be done. So it comes out as 125 into 10 to the power 6 into 1.65 into 0.034 lb per day. The lb here is not cancelled out, it is there, lb per day. So if we convert into mass flow rate per hour, it will be 125 into 10 to the power 6 into 1.65 into 0.034 divided by 24 lb per hour. So if we calculate this, will be 2 2921187.5 equal to 2.9 into 10 to the power 5 lb per hour. So the correct option is 2.9 into 10 to the power 5 lb per hour, option 4. So copy down the numerical, then we'll be going to the next numerical. Okay, we'll be going to the next question. So, so the same data. The next question is liquid flow rate at separator condition for water and hydrocarbon liquid respectively are option A 175 in and 11540 lb per hour, 1450 into and 20,300 lb per hour. Option C is 2500 and 1,55,670 lb per hour, and option D is 28600 and 562,000 lb per hour. These are the four options. Just try once from your end, then I'll be solving it. Okay, let me solve the question for you. So, okay, so for water, W water equal to 0.5 divided by 100, whole thing into 2.9 into 10 to the power 5 lb per hour equal to 1450 lb per hour. Next, for oil equal to 7 by 100 into flow rate is 2.9. This we have already found out in the previous question, the mass flow rate. So we'll be using it here. So if we solve it, The answer should come out as 203,220 lb per hour. So the correct option is 1450 and option B 203,300 lb per hour. Copy down the numerical, then we'll be going to the next question. Okay, we'll go to the next question. Question 6. The liquid mixture density at separator condition. It is continuation of the main data. This is the data given. So with this data only we are doing all these numericals. So now the third question is the liquid mixture density at separator condition is, the four options are: option A 101.15 lb per feet cube, 78.34 lb per feet cube, 54.68 lb per feet cube, and 25.87 lb per feet cube. These are the four options. Okay, so now I'll be solving. So the flow rate for mass flow rate for water is 1450 lb per hour. Mass flow rate for oil is 20300 lb per hour. We have found this in our last question. Density of oil equal to 54.15 lb per feet cube. Density of water equal to 62.1 lb per feet cube. So density of liquid equal to 54.15 into 20300. This is the formula for finding the density of the liquid mixture. 50 plus 62.1 1450 20300 plus 1450. So if we solve this, the answer should come out as 54.68 lb per. So this is the density of mixture in the separator. It is 54.68 lb per feet cube. So note down the numerical. Then we'll be going to the next question.
Sir, done.
Okay. Okay, then we'll go to the next question. If a missed limiter is added to the separator, the vertical terminal velocity is k equal to 0.308. It is given. The four options are option A 0.75 feet per second, option B 1.25 feet per second, option C 2.73 feet per second, and option D 4.25 feet per second. If a missed eliminator is added to the separator, the vertical terminal velocity you have to find out. Try once, then I will solve it. 2 minutes I will be giving. Just try to solve. Okay, let me just solve it directly without wasting much time. So for finding the terminal velocity, the formula is k equal to density of liquid minus density of gas divided by density of gas. So then k is given as 0.308, then density of oil is 54.15 minus 0.68, density of gas is 0.68 equal to 2.73 feet per second. So this is the velocity, terminal velocity 2.735 feet per second. The correct option is option C, 2.73 feet per second. Write it quickly, then we'll go to the next question.
Sir, your slide is not properly visible.
Slide is not visible. Just wait. Is it visible now? Let's see if it's visible now.
No,
Not visible. Shubham, is it not visible to you also? Can you get here? From my side, is it visible? Just
no.
not visible. Shubham, Can we just disconnect once and continue? Because from my side, there is no problem, but I don't know why it's not showing. If you're still facing the problem, just can you just okay? We'll go to the next question. Shubham Pajwal will join us. The settling velocity of heavy fluid is assuming droplet size to be 89 micrometer, k equal to 0.163. Four options are A 2.05 inch per minute, 5.25 inch per minute, 7.54 inch per minute, and 10.628 inch per minute. So these are the four options. Okay, so let me solve it. If we don't have much time left. So the formula for this is EHK into VW. So it will be 0.163 into 62.1 density of water minus 54.15 by 0.63. 2.05 inch per minute. So the answer is 2.05 inch per minute, which is option C, option A, 2.05 inch per minute. So note down this. Are you able to see now, Prajwal? Prajwal, let me know if you are able to, if you are still facing
Sir.
difficulty. Is it
Yes,
visible?
yes.
Okay. Okay, so let's go to the next question. The rising velocity of light liquid from the heavy liquid is for droplet size 89 micrometer, K equal to 0.163 R. 0.163 is the four options at 0.55 inch per minute, 1.66 inch per minute, 2.74 inch per minute, and 3.67 inch per minute. Try once from your side, then after 2 minutes I will be solving it. Okay, let me solve this one. These all questions are based on very short formulas, so but there are good chances that this all may come in your exam. So the formula is VR equal to A into density of water minus density of oil, 0, 0.163 into 62.1 minus 54.15, 1.66 is the answer. So the correct option is 1.66 inch per minute. Just copy down this one. Okay, let's go to the next question. Question 10. The settling time for heavy and light liquid through a settling distance of 1.5 feet and rising height of 0.8 feet. The four options are 0.85 minute and 4.78 minute. Option B 2.35 minute and 6.79 minute. C 5.26 minute and 10.45 minute. And option D 8.78 minute and 5.78 minute. These are the four options. Write down the question. Okay, let me solve it. Formula is TSHL equal to 12 into HL VHL equal to 12 into 1.5 divided by 2.05 equal to 8.7 8.78 millimeter. And for the light liquid, this one we have find the settling time for the heavy liquid. For light liquid LL, it will be 12 into HH velocity of light liquid. So it will be 12 into 0.8 divided by 1.66. So this should come out as 5.78 millimeter. So the correct option is option D, 5.78 minute and 8.78 minute and 5.78 minute. Sorry, this will be minute. Minute. Just write down the numerical, then we'll go to the next question. Okay, I will go to the next question. So it is a theoretical question. Vertical separators are used for four options: low gas well ratio, intermediate gas well ratio, high gas well ratio, or none of the above. Tell me, I have already discussed it in the revision part. So the
B.
correct option
Intermediate
will
gas
be
oil ratio.
intermediate. Uh-huh. Prajwal?
B.
Yeah, yeah, correct, correct. The correct option is B, intermediate gas well ratio. Very good. Next, we'll be going to question number 12. Match the following separator components with their functions. On the left side, there are centrifugal device, disengagement section, and mist extractor. Centrifugal inlet device. Number 2 is disengagement section, and number 3 is mist extractor. On the right side, the options are to allow liquid droplets to settle out of the gas stream. Option B is to coalesce small particles of liquid, and option C is primary separation of gas and liquid occurs. The four options are
Option
1C,
first.
2A, 3. Which one, Prajwal?
First option.
First option. Okay, let me just see. The four options are 1C, 2A, 3B. Second is 1C, 2B, 3A. Third is 1A, 2C, 3B. And the fourth is 1A, 2B, 3C. Correct option is option 1. Very good. 1C, 2A, and 3B. Next, we'll again go to numericals. A gas is flowing at a rate of 10 mmscf per day through a separator of diameter 2 feet. A condensate of API gravity 67-degree API is flowing at a rate of 30 barrel per mmscf. The operating condition is 800 psi G and 75 degree Fahrenheit. Considering gas compressibility factor to be 0.7, K equal to 0.21 and density of gas to be 0.35 lb per feet cube and density of liquid is 62.3 lb per feet cube. The question is superficial gas velocity based on total cross section area. Four options are 8.85 feet per second. Option B is 7.23 feet per second. Option C is 2.76 feet per second and option D is 5.54 feet per second. Write down the question. Okay, I will be solving it. I won't waste much time. There is not much time left. So, the formula for this is velocity equal to V equal to K root over density of liquid minus density. This type of numerical we have done a lot today. So mainly this type of numericals will come in your exam. So be prepared. 62.3 minus 0.035 density of gas divided by 0.035 equal to, if you solve this, it is 8.85 feet per second. So the correct option is option A, 8.85 feet per second. Just write down. I'm giving you 2 minutes. Then we go to the next question.
Done.
Okay. So next we'll go to the next question. Question is gas capacity at standard condition for a vertical separator. The four options are 30, option A 36.82 mmscfd, option B 116.75 mmscfd, option C 94.35 mmscfd, and option D is 181.64 mmscfd. These are the four options. So let me solve it directly without delay. The formula for gas capacity is equal to 2.4 into d square into k into p divided by z into p plus 460. We have already done one type of numerical like this today. So this is another density of liquid by density of gas divided by density of gas. So if we solve this, it will be 2.4 into 2 square into k is 0.21 into 800 pressure divided by z is 0.7 into 75 plus 460. will be 62.3 minus 0.035 divided by 0.035. So if you solve this, so the answer I am getting is 181.64 mmSCFD. So 181.64, the correct option is option D, 181.64 mmSCFD. Quickly note down, then we'll be going to the last set of questions. Another two questions are left. Okay, let's go to the last set of questions. A natural gas field is producing 130 mmSCFD of gas of specific gravity 0.8. The wellhead pressure and temperature are 120 degree Fahrenheit and 450 psi respectively. And the fluid density and formation volume factor are density equal to 1.60 lb per feet cube and Bg equal to, that is formation volume factor of gas, equal to 0.038 feet cube per SCF respectively. The separator operating conditions are 150 psi and 107 degree Fahrenheit. The mixture contains 0.48% water, density equal to 62.1 lb per feet cube. Viscosity is 0.63 cp and 8% hydrocarbon liquid, density of which is 57.15 lb per feet cube. Viscosity is 0.78 cp and the remaining gas of density is 0.66 lb per feet cube. And kinematic viscosity is 0.1. Okay. Kinematic viscosity of 0.012 cp. The hydrocarbon liquid hold up and search time are 28 minutes and 4 minutes respectively. So first question is 15. Considering k equal to 0.308, the vertical terminal velocity after addition of mist extractor is option A 2.84 feet per second, 1.72 feet per second, 3.58 feet per second, and option D is 7.34 feet per second. Write down the question. Okay, let me solve it. That is VT equal to K density of liquid minus density of gas divided by density of gas. 0.308 57.15 minus 0.6666. So if we solve this one, we should be getting answer as 2.84 feet per second, which is option A, 2.84 feet per second. Let's write down. Next we'll be going to the next question. Last question. Okay, so this is the last question for today. The settling velocity of heavy fluids, assuming droplet size to be 89 micrometer, is first option is 2.84 inch per minute. Option B 1.28 inch per minute. Option C is 3.72 inch per minute, and option D is 0.94 inch per minute. So I'll be directly going to solve the numerical because there is no time left. So it will be heavy liquid velocity of heavy liquid equal to K into density of liquid minus density of heavy liquid divided by viscosity. So it will be 0.163. There is little bit of changes in all these formulas. So be careful while using the formulas where you should know which formula to put. Okay. So 57.1 this point 0.15 divided by 0.63. So if you solve this one, the answer should come out as 1.28 inch per minute. 1.28 inch per minute. So the correct option is 1.28 inch per minute, option B. Okay. So thank you. That's all for today. Next, we'll be meeting next Tuesday with sixth week assignments. So till then, take care. Good night.